So we say X follows binomial distribution with parameters n comma p if X represents the number of success occurred in n independent Bernoulli trials. Right? And this is how we denote. So here we simply say that X follows binomial distribution. With parameters n comma p. I'm not writing that. Okay, let me write with parameters n comma p. Okay, and this is the notation for binomial distribution. And what is the probability mass function of it? So probability mass function of a binomial distribution that is nothing but probability that X is equal to I, which is given by n choose I, this into p power I into 1 minus p, or you can write q as well. So n minus I, where I equal to 0, 1, 2 and so on up to n. Yeah. So now we have to check that whether it represents a probability mass function or not. We have to look at the properties of probability mass function. What are the properties? We want this p of x, this is to be greater than or equal to 0. Yeah, there is no doubt this expression is always greater than or equal to 0. So the first condition, fine. And the second one, summation of p of x, this must be equal to 1. So this we have to verify. So let me verify whether it is true or not. So what is it? I have to see summation over I, where I is running from 0 to n, probability that x equal to I. That's what exactly equal to summation I equal to 0 to n. This is n choose I into p power I into 1 minus p whole power n minus I. Now this is exactly looking like the binomial expansion of x plus y. Here you can see x plus y whole power n is given this way. So if you compare with the first one, in place of x I have p here, and in place of y you have 1 minus p. So once if you substitute it, you'll get this is x, that is p, plus y, which is 1 minus p whole power n. But p plus 1 minus p, this will give you 1. So 1 power n, this is 1. That's it. So the second condition is also satisfied. So clearly there is no doubt this represents a probability mass function. Okay. So now let us try to answer this question. So here is the question. A multiple choice test consists of 8 questions with 3 answers to each question, of which only 1 is correct. So you could see that there are 8 MCQs. And now each has 3 choices. And only 1 is correct. Okay, so now if you answer this question randomly, then the probability of getting success is 1 out of 3, isn't it? So here we can clearly define what is the probability of getting success. Getting success, marking the correct answer. Okay, so that is actually 1 out of 3. Why? Because there are 3 choices, so the chance of getting success is 1 by 3. And of course, you can see what is the chance of getting failure. No need to write, that is 2 by 3. So here let me take it as P. So now answering each MCQ, you can take it as a Bernoulli trial. Why? Because when you answer first MCQ, the result is either it is a success or a failure. Either you'll get correct or incorrect. So that is a Bernoulli trial. So here you are performing Bernoulli trials 8 times. Okay. So now if I define my random variable x to be the number of correct answers then definitely x represents a binomial distribution with parameters 8 comma 1 by 3. Why? Because the probability of getting success is 1 by 3 and we are performing 8 trials. This is what. And if you look at the other information, a student answers each question by rolling a balanced die and checking the first answer if he gets 1 or 2, and second if he gets 3 or 4, and third if he gets 5 or 6. It means, see, this actually denotes that the student is not choosing any option intentionally. This is completely a random experiment. And he is performing a random experiment in such a way that for each option he is giving equal importance. See, if he gets 1 or 2, he is picking the first option. So the chance of picking the first option is 2 out of 6. Why? Because when you roll a die, there are actually 6 outcomes. So if he get these 2 outcomes, he is picking 1. So the chance of getting choosing 1 is 1/3. So this is same as 1/3. Similarly, 3 or 4, the chance, if he get 3 or 4, he checks the second option, and the chance of checking the second option is 1/3. Why? Because 2 by 6, that is 1/3. Similarly, the other. Okay, so he is performing a random experiment in such a way that all outcomes are given equal importance. That's what he do. Okay. So now to get a distinction, the student must secure at least 75%. So, okay, 75% correct answers. If there is no negative marking, what is the probability that the student secured distinction? So it means if you want to get distinction, 75% correct answers must be there. So now you tell me what is actually 75% of 8? What is 75% of 8?
Six, sir.
That is 6. Yeah. 50% is 4, 25% is 2. You can simply see that 75% is 6. Okay. So he need to get at least 75% correct answers. It means we do expect this. What is the probability that x greater than or equal to 6? It's not that x is exactly equal to 6. We want at least 6 answers to be correct. So they can be 6 or 7 or 8. So if he gets 6 answers or 7 answers or 8 answers correct, definitely he'll get a distinction. So this is what we need to calculate. Probability that x greater than or equal to 6. X greater than or equal to 6, it means it may happen that x is equal to 6 plus and x equal to 7 plus probability that x equal to 8. So this is what. Now you know x follows binomial distribution with these parameters. Now we can easily calculate. So you want 6 answers to be correct. So this is 8 choose 6 into 1 by 3 whole power 6 into 1 by 3 whole power 8 minus 6, that is 2, plus 8 choose 7 into 1 by 3 whole power 7 into 1 by 3 whole power 8 minus 7, that is 1, plus 8 choose 8 into 1 by 3 whole power 8 into 1 by 3. Oh, what am I doing? It is 1 minus 1 by 3, so it must be 2 by 3. So this must be 2 by 3. This must be 2 by 3 power 0. Why? Because p is equal to 1 by 3, then 1 minus p, that is 1 minus 1 by 3. So that must be 2 by 3. So this is what q. Okay. So now 8 choose 6. I hope you know this formula. NCR, which is same as n choose n minus r. It means selecting r elements, it is same as deleting n minus r elements. Okay, so now 8 choose 6, which will be same as 8 choose 2. 8 choose 6, this will be same as 8 choose 2, and it is easy to calculate 8 choose 2. So that is 8 into 7 into 1 into 2. So this is 4. So 4 times 7, you'll get 28. 28 into 2 square, that is 4 divided by 3 power 8. Plus, now 8 choose 7 is same as 8 choose 1. So this is 8 into 2 by 3 power 8. Plus, this is 8 choose 8. That is only one way we can do that. 1 by 3 power 8. Can you tell me what is the final answer for this?
And 0.19.
So you're saying it is 0.019. So approximately I can say 0.02, isn't it? So it means, what is the chance? There is only 2% chance that he'll get distinction. So the probability that he secure a distinction is 0.02. It means there is only 2% chance that that guy will get a distinction. So it is very, very less. You could say almost no. There's no chance that he'll get a distinction. And if you look at the chances that he'll not get a distinction, we can say that is 98%. Okay, and if you increase these 3 options from 3 options to 4 options, then the probability may become very, very small. And even if you increase it to 5 options, then it becomes very, very less. It's like almost 0.00 you may get. Okay, why? Because the probability of getting success is decreasing here when you increase the options. So if you have 3 options, this is 1/3. If you have 4 options, this is 1/4. If you have 5 options, this is 1/5. The probabilities are getting decreased when the options are more. Okay. So let us look at one more problem. Now this is an easy problem. 10 coins are tossed simultaneously. Find the probability of getting at least 7 heads. You could see the random experiment. 10 coins are tossed. Now each one you can take it as a Bernoulli trial. Right? So 10 Bernoulli trials are performed. So they're asking what is the probability of getting at least 7 heads. So now you can define your random experiment, and you can define your random variable. Random variable is number of heads appeared. So number of heads occurred. So this you can take. So now we can clearly see that X follows binomial distribution with parameters 10, the probability of getting success is 1/2. Now what they're asking is probability that X getting at least 7 heads. It means probability that X greater than or equal to 7. And you know how to answer it. So probability that X equal to 7 plus probability that X equal to 8 plus probability that X is equal to 9 plus probability that X equal to 10. I hope you know how to compute them, right? So I'm leaving it to you. Next. So, and manufacturer of pins knows that 5% of his product is defective. If he sells pins in boxes of 100 and guarantees that not more than 10 pins will be defective, what is the probability that a box fails to meet the guaranteed quality? So you should carefully think what must be your random variable. So how you should define. First, understand this question. See, he knows the 5% of them are defective. And he is selling pins in a box of 100 and guarantees that not more than 10 pins will be defective. So now you could take it this way. So in a box you are keeping 100 pins. Now what is our interest? We'd like to know whether each pin is defective or not. So when I pick up one pin, my interest is to see whether it is defective or not. If it is defective, I'll term it like this. If it is defective, I'll term it as a success. My random experiment is success. Why? Because my random experiment is to check the number of defective pins. The moment I get defective pin, I'll treat it as a success. If it is a good pin, I'll treat it as a failure. Okay, so now let me define my random variable X that represents the number of defective pins. I hope you understand what is my random experiment. It is to look for a defective pin. So when you select a pin from these 100 pins, so you're looking whether that pin is defective or not. Okay, so X represents the number of defective pins, and I can say that X follows the binomial distribution with parameters n comma p. So I should tell what is n here. Since there are 100 pins in a box, so we'll take n to be 100. Okay, and what is the probability of getting success? So I need to find what is P. That's what probability of finding a defective pin. And we know 5% of the product is defective, so therefore the probability of finding defective pin is 0.05. So this is P. Okay, so therefore n equal to 100 and P is equal to 0.05. So now what is the probability that the box failed to meet a guaranteed quality? But what is the guaranteed quality here? Not more than 10 pins will be defective. It means he guarantees that at max he can find 10 pins defective, not more than 10. It means when you perform this random experiment, X cannot exceed 10. That's what it says. Now, if you want to check this probability that this condition fails, it means we need to check what is the probability that X will exceed 10. So that is probability that X strictly greater than 10. What it represents, this is what exactly represents the probability that more than 10 pins are defective. isn't it? So once if you have this, it means if the more than 10 pins are defective, it means this guaranteed condition failed. Okay. So now let me calculate what is the probability that x greater than 10. But here if you observe that n is actually 100. So if you want to calculate it, you need to take 11, 12, 13, 14, 15. You need to go till 100. There are many terms to write, right? But it's not good to go that way. So what we'll do is we'll write it like this: 1 minus, from the properties of probability mass function, we can write it as 1 minus probability that x less than or equal to 10. This is what you can do. So when you are dealing with the discrete random variables, you should give importance for equal to. Okay, if it is continuous, not an issue, but discrete, you should take care of it. So now you know how to do it. 1 minus this one can be written as summation I is equal to 0 to 10 probability that x is equal to 10. Sorry, x is equal to I. It means less than or equal to 10, it means you need to take 10, 9, 8 up to 0, right? So now this is same as 1 minus probability that x is equal to I. Let me write summation I is equal to 0 to 10. What is it? So this is 100 choose I into 0.05 whole to the power of this is I into 1 minus 0.05, that's what 0.95 whole to the power of 100 minus I. But here there is a problem. We may face a problem with our calculators, because if you look for 0.05 whole power 10 in the calculator, it is almost 0.0000. Okay, and when it comes to this guy 100 choose, let's say if I look at 9, this is very big value, and whereas this is very small value. When you multiply these two, okay, you'll get a value, that is fine, but our calculators may not give you the good result here. Okay, so here in this case for 100 itself we are facing difficulty. What happens if I have 1000 here, if I have 10,000 here? So then in that case it is difficult to calculate these things, right? Okay, now if you have this situation, so Poisson will help us to overcome this situation. So let me tell what it is. So now the question is, if n is large, you know that x follows binomial distribution with parameters n comma p. Now the question is, if n is very large and p is very small, then what can you say about this? N choose I into p power I into 1 minus p whole power I. So what happens to this? It means, in other words, this is what we are interested in. As n goes to infinite and p goes to 0, okay, what happens to this expression? It's no need to say that p goes to 0 as n goes to infinite, and here you know that p is small, very a small value of p. So in this case, what happens to this expression? So now it is found that this expression converges to e power minus lambda into lambda power I by I factorial. This is where it converges, where lambda is equal to n into p. Okay, so it is found that as n goes to infinite when p is small, this entire expression converges to this guy, e power minus lambda into lambda power I uh, by I factorial. Okay, so now if you look at this probability, that is, this is what exactly probability that x is equal to I. So now the probability that x is equal to I will go to e power minus lambda into lambda power I by I factorial. Okay, so when you know x follows binomial distribution with parameters n comma p, when n is large, p is small, you can replace this probability mass function with this mass function. And this is what we call, if x has this kind of probability mass function, we say it follows Poisson distribution. And we say x is a Poisson random variable. So let me define what is a Poisson random variable. A random variable x with the following probability distribution function, probability mass function, sorry. Where the mass function is given like this: probability that x is equal to I, which is equal to e power minus lambda into lambda power I by I factorial. Okay, where this I will be going from 0, 1, 2, 3, 4 and all. But because we are saying that we derived this as n goes to infinite. Okay, and here you could see what is lambda. Lambda is actually n into p, and this is the information we can write it when you know x follows binomial distribution with parameters n comma p. Okay, so whenever you have a binomial distribution where n is large and p is small, you come to Poisson distribution. Okay, so now here, see in the last case, it is easy to calculate this expression, that is this is equal to 1 minus, let me write it here, 1 minus summation I is equal to 0 to 10. Now this one will be replaced with e power minus lambda. What is lambda here? So lambda is actually equal to n into p. That's what 100 into 0.05, and that's what exactly 5, isn't it? So when lambda is 5, so this is e power minus 5 into 5 power I by I factorial. Now it is easy to calculate these expressions. So now you calculate this expression, so this will give you the approximate value of this. I don't say this is exactly equal to, this is approximately equal to this. Okay, so a random variable with this probability mass function, which is called a Poisson random variable. Okay, so we use this Poisson random variable when you know x follows binomial distribution if n is large and p is small. And also we use this Poisson distribution when you are dealing problems related to number of typo errors in a page. If you take a book, and there my interest is to see the number of typo errors in a particular page. Okay, and similarly let me show you some other situations where we use this Poisson distribution. So here you can see some real life examples where we use the number of defects in a packet of 100 plates, like that's what we did right now, and the number of telephone calls received at a particular telephone exchange in some unit of time, number of print mistakes in a page of a book, and the number of fragments received by a surface area A from a fragment atom bomb, and the emission of radioactive particles, and the number of air accidents in some unit of time. So these are the situations where we use these Poisson distributions. Okay, so I hope you understood what is a binomial distribution and what is a Poisson distribution. Now let us talk about their expected value and the variance. So first if x follows binomial distribution with parameters n comma p. Now my question is, what is the expected value of this? And of course, when I ask expected value, definitely I look for what is the variance. What is the variance of x? Okay, so first let us go for finding expected value. Now expected value of x, that will be given by summation over I. You know, for binomial it goes from 0 to n. So this is I into probability that x is equal to I. Isn't it? Now this is exactly summation I equal to 0 to n. So I into, we know what is probability that x is equal to I. So that is n choose I into this is p power I into 1 minus p whole power n minus I. So now we have to simplify this summation, then we should write the final guy, right? See here, if I don't have this I, then our life is very easy, isn't it? Why? Because this is exactly summation p plus 1 minus p whole power n. So let me try to get rid of this I. So for that, we have a formula. So that says n choose I. Can I write it like this? N choose I is nothing but n factorial by I factorial into n minus I factorial. Now this one I'd like to write it like this. So n divided by I into, so if you take n common here, then you'll have n minus 1 factorial by, if you take I common here, I factorial, and this is n minus I factorial. Now you could see that the second expression, which is actually equal to n choose I, sorry, n minus 1 choose I minus 1. Okay, if you don't believe, let me take one more step. So this is n divided by I. So this one can be written as n minus 1 factorial by I minus 1 factorial, this into, can I write it like this? N minus 1 minus I minus 1 factorial. Minus 1 gets cancelled, so you'll have just n minus I only, there is no change. But this one, which exactly looks like n minus 1 choose I minus 1. Okay, so this looks like n minus 1 choose I minus 1. Now you can replace this n choose I with this guy. So the moment I replace, now the expected value of x, so expected value of x will be equal to summation I equal to 0 to n. This is actually I into n by I into n by I. Now this is n minus 1 choose I minus 1 let me use this bracket. So n minus 1 choose I minus 1 into p power, you have I into 1 minus p whole power n minus I. Okay, you can cancel this I and you can take this n out. So let me take it. So if I take n out, summation, so I equal to 0 to n. So now this is n minus 1 choose I minus 1, this into, I'd like to do one thing. Since I have n minus 1 choose I minus 1, I'd like to have p power I minus 1. Okay, so if you have p power I minus 1 here, so you should introduce one more p here. So into p, so into you have 1 minus p whole power n minus I. Now you can take n into p out. So if you take n into p out, so this is what you have, n equal to 0 to n. And of course you could see that n minus 1 choose n minus 1. Is anything missing here? No. So let me write it like this. I equal to 0 to n. This is actually n minus 1 choose I minus 1 into, this is p power I minus 1 into 1 minus p whole power n minus I. Now can I say this is nothing but n into p? This is what the expansion of p plus 1 minus p whole power n minus 1. P plus 1 minus p, which will give you 1. So this is simply np into 1 power n minus 1. So that's what n into p. Therefore you can conclude that if x follows binomial distribution with parameters n comma p, then the expected value of the distribution is nothing but n into p. So every time we don't derive, we simply use this formula. So if you want to know expected value of a binomial distribution, that is exactly n into p. That's it. Okay, so use the similar analysis and try to find this. What is the variance of x? So to calculate variance of x, there are two things you need to calculate. One is expected value of x square and other one is expected value of x. Anyway, this is readily available. Why? Because we calculated here, right? So the variance of x is nothing but expected value of x square minus expected value of x whole square. This is the formula for variance.